Having now looked at how to evaluate integrals by creating antiderivatives and using the fundamental theorem to sub in the upper and lower limits, it's worth revisiting why we want to compute integrals at all. So when we see something with an integration from a to b of some function, one of the things we can imagine that is the area underneath the graph. So if we integrate from a to b, some function f of x dx, that translates to the area under the graph between a and b, that area there, assuming it's positive with negative contributions if things were below the axis or the function values were negative. Now, there's not a lot of times in engineering and physics where we really need areas precisely, so it's worth reminding ourselves where we started with. When we integrated velocity over time between 2 points, and again it was 2 time points, then it gets a little more interesting. What do we get when we integrate the velocity from time A to time B? We get what this net change theorem here tells us, the net change in the antiderivative of velocity, which would be position, between time A and time B. So key thing here is that the integral doesn't tell us our position, it tells us the change in the position. So the delta s, if you like, in the knowing the velocity, the delta s, or the change in position, is what we get out. More formally, if we're trying to track some quantity, so again here this was position at B minus position at A, that's a change in position, then the integral of the derivative, that would usually be called v. We're not in vectors though, so no vector. If we integrated v over some time interval with respect to time, that would give us the change in s, or s of b minus s of a. So that's a handy thing to have in mind whenever we're trying to compute some kind of total effect or total change, or, as it says here in the notes, an accumulation. So keep that in mind as we go forward. Here's a quick concept question to test yourself on this. If h of t is the height of a child in centimeters at time t in years, and it started at 120 centimeters, the child started, he or she started at 120 centimeters at age 10, how would you represent the amount the child grew between that time and 8 years later when they reached 18? So take a look at the forms here, think about that net change theorem, pause the video, and we'll explore it in a second. Okay, so if we're looking at the net change in height, well, that would be the difference between the height at 18 years and the height at 10 years, which would be a change in h. And the net change theorem says, well, we would get that by integrating from t equals 10 to t equals 18. And the key thing is, what do we put inside the integral? Well, we put h prime of t dt. Now, if that seems like an artificial or an artifact of symbols, remember where this comes from. These heights here are centimeters. This integral is equivalent to a sum of something with delta t's. And if you think of the units of time here, we're going to be talking years, then if we want centimeters at the far end, we better have units of centimeters per year in front of our time units. And so the only way for that to work would be to have h prime of t in there. H is in centimeters, its derivative with respect to time would be centimeters per year, and then we get a nice product giving us centimeters back. If we look in contrast in the units here, we get centimeters times years. Adding those up, I'm not entirely sure what that would give you, but certainly nothing that answers the question that was asked here. We're almost done. This gives us the change between, change in the child's height between 18 years and 10 years. And that's actually all we need. So in fact, this is the answer, C. Answer D is close. There was another additional fact here, which was that the height is 120 centimeters at age 10. The answer D here is equal to the height, the child's height, at age 18, which is of course equal to the height at age 10 plus the change between t equals 10 and t equals 18. And that's what we just computed earlier. So if we want to take our 120 here, sorry, I should put all this in brackets. If we started at 120 and we gained the integral value, h prime of t dt, that would give us the net height at age 18. But if we're just interested in the difference, the net change theorem says the integral itself tells us how much our quantity has changed if we integrate the rate over some particular interval like this.